Hello there. Welcome back. We continue with logic coverage criteria into week 6. This is the third lecture. We saw examples of logic coverage criteria applied to source code. We saw two examples, thermostat, where we analyzed the predicates using logic coverage criteria that we learned. Type of a triangle, where we had lots of predicates which we analyzed using some of the logic coverage criteria that we learned. In the last lecture, you saw how certain specifications can be naturally written as logical predicates, and in fact most of them come in either conjunctive normal form or disjunctive normal form, where it becomes easy to write test requirements for active clause coverage. And we saw that using logic coverage criteria, you could test for those sequencing constraints as preconditions or postconditions to be true. There are more kinds of software artifacts where logic coverage criteria come into picture. One such artifact is that of a finite state machine. If you remember, we had introduced finite state machines when we did graph-based testing. They are basically special kinds of graphs that have states which are represented as the vertices of the graph, transitions which connect vertices through edges, and they are popular graph models for specification, for design, and so on. So while we analyze them as graphs when we did graph-based testing, it's important to note that the transitions or the edges of the finite state machine also have guards in them, which describe conditions under which a particular transition can happen or not happen. So a state machine has to transition from a particular state, say state 1, to another state, state 2, then if the transition has a guard associated with it, then the condition of the guard, which is given as a logical predicate, is tested first. And if it is true, then only the transition can be taken and the state change happens. So while we considered them as graphs earlier, now we focus on the guards that come in the transitions of the finite state machine, which are typically logical predicates for us, and see if we could apply logic coverage criteria to test finite state machine specifications by focusing on the guards in the transition. So again, like we've been doing, we'll take an example and understand how it is done. So here is a finite state machine. Let's first spend some time understanding this finite state machine. It has 4 states. The initial state, which is down below here, marked by an incoming arrow, is all doors closed. Then there is left doors open, another state, right doors open, another state, and all doors open, which is another state. So this is a state machine that describes the status of the doors of a train that goes on a subway. It could be a metro train, or it could be any passenger train that goes on a subway. Typically, subway trains have doors on both sides of the train. A particular station might have compartment on the left-hand side. A particular station might have compartment on the right-hand side. Certain stations could have compartments on both sides. So based on the availability of compartments for the passengers to embark and disembark, the left doors or the right doors or both the doors should be open. When the train is moving, let's say it's inside a tunnel because it's a subway, that is, when it's not in a station, then all the doors should be closed. So this is a state machine that describes the status or the way the doors of a train that is going on a subway behave. So the initial state says that how many ever doors are there, all of them are closed. From that state, you could take a transition through this edge, the left-hand side, to a state where left side doors all open up, or from all doors closed, you could take a transition to a state on the right side where the right doors open up. Both these transitions have a detailed guard that is labeling them, which means that this transition can be taken only if this condition or guard becomes true. Similarly, I can go from left doors open to all doors open provided another kind of guard is true, or from right doors open to all doors open provided another guard is true. And finally, I can transition back from all doors open state to all doors closed state, provided another guard is true. So let's understand the guards one at a time and see what they say. So we start with the initial state, all doors are closed. Let's say I want to go to a state where the left doors become open. This transition comes with a guard in it. Let's read the guard, the condition, to see what it is. It says train speed should be equal to 0. That makes sense. The train should not be moving. So the speed of the train should be 0. Next it says platform should be equal to left. Read it as platform is on the left hand side. And the location of the train should be inside the station, in station, or emergency stop is there, override open is there, and location is in tunnel. So how do you read this? I can transition from a state where all the doors of the subway train are closed to a state where the left side doors of the subway train are open, provided this guard or condition is true. So let's read that same guard once in English to understand. Train speed should be equal to 0. Train is not moving. Platform is on the left hand side. That's the second clause. And the location of the train is inside the station, or somebody has pressed the emergency stop button and opened the door manually using the override option while the train is still inside a tunnel. Is this clear? So you can open the left doors provided the train is not moving, platform is on the left side, and the train is in the station, or there's an emergency, the train is in the tunnel, somebody's pressed the emergency stop and done a manual open. Symmetrically, you can go from state all doors closed to right doors open. If the train is again not moving, train speed is 0, platform now is on the right hand side, the location of the train is inside station, or somebody has pressed emergency stop and override open and the train is located in the tunnel. This is symmetric to the left doors open. Now when the left doors are open, I can transition to a state where all doors are open, provided I find the second platform on the right hand side also. Symmetrically, from the state where right doors are open, I can transition to a state where all doors are open, provided there is another platform on the left hand side. Finally, I can move from the state all doors open to all doors closed, provided this guard is true. That is, there is no emergency stop. Read this little symbol as negation. Remember, I had introduced it to you in the first lecture in logic. Not of emergency stop. That is, emergency stop does not hold. Override open does not hold. Negation of override open. Doors have been cleared. And close door button has been pressed. Doors have been cleared in the sense there are no passengers or anybody moving across the doors. So the doors have been cleared to be closed and somebody has pressed the close door button. So here is a finite state machine that has 4 states, 5 transitions. Each of the 5 transitions have a guard associated with them, which describes the conditions under which the transition can be taken, and based on whether the guard is true or not, the transition may or may not happen. Each guard is our good old logical predicate, that is a logical combination of one or more clauses. So we can apply logic coverage criteria that we learned to test for these clauses. So let's take one of the predicates. Let's say we take this predicate on the left hand side. Train speed is 0. Platform is on the left hand side, location of the train is inside the station, or emergency stop button and override open has been done and the location of the train is inside the tunnel. This occurs as a guard in the transition from the state of all doors being closed down below here to the state of left doors being open. This predicate, as you can see here, if you count, has 6 clauses. So predicate coverage in this predicate will basically tell you one test requirement for the predicate being true, one test requirement for the predicate being false, and it will tell you whether or not the transition can be taken. It can be taken only if the predicate evaluates to true. If the predicate evaluates to false, then the transition cannot be taken. So that's fairly simple. Now let's try to apply one more logic coverage criteria that we learned. Let's say we try to apply active clause coverage criteria for this predicate. Remember, this predicate has 6 clauses. So you do the usual thing of per clause determine the conditions under which the clause determines a predicate. Usually we substitute, give shorter names like A, B, C, D for clauses. Then remember, substitute the concerned major clause with true, substitute the major clause with false, XOR the result. So I am not showing the working out, and neither am I substituting here. What we've done is I've directly given you the formula. It'll be a good exercise for you to work it out. But let's consider one of the clauses. Let's say the train speed is 0. For this clause to be a major clause, the conditions under which this clause will be a major clause and will determine the predicate are given here. If you do the working out that I just described, the resulting predicate will be this. Platform is left and location is in station, or emergency stop and override open and location is in tunnel. Similarly, take some other clause. Let's say we take the clause override open here, the 5th clause in this predicate. So again, work out the same thing. Substitute it with true, substitute it with false, XOR the result. The resulting formula will be this. Train speed is 0 and platform is left, and it's not the case that location is in station and emergency stop holds and location is in tunnel. So similarly, you can compute it for all the 6 clauses, with each of them taking turns to be the major clause. So this resulting formula will describe precisely the conditions under which the considered clause as a major clause will determine the predicate. So now we've written out. So we can write general active clause coverage criteria, correlated active clause coverage criteria, or restricted active clause coverage criteria. Let's say we choose correlated active clause coverage criteria, CACC. So these are the 2 clauses that I had considered in this slide: train speed 0, override open. And these resulting formulas describe the conditions under which the clause determines the predicate. So if the major clause was train speed 0, major clause being true, major clause being false, which I have written as not of train speed equal to 0 is train speed not equal to 0. And then the conditions under which the remaining clauses: platform is on the left side, train is in station, emergency stop button is pressed, override open button is pressed, train is in tunnel. Similarly, for the second clause here, for the override open, the clause is made true once, the clause is made false once by negating it. That row I have expressed it in true and false. The rest of the predicates I assign true false values such that the major clause override open determines the predicate. So this is the table for that. So I've just illustrated it for the 2 clauses that we considered in this slide. But there are totally 6 clauses. Just as we said, you can compute the conditions under which each of the 6 clauses determine the predicate. You can also compute CACC test requirements for each of the clauses to be a major clause. Now, out of these 6 clauses, this was all right? So this is your test requirement, and you should be able to write test cases giving true false values and actually test the behavior of the finite state machine. Now let's see what the other problem is. So this predicate had 6 clauses, right? There is some inconsistency in the specification of the finite state machine in the way these conditions are written here. While we were reading out and understanding them, it all seemed all right, but there is a small inconsistency, and that inconsistency can be revealed by doing active clause coverage criteria testing. Specifically, if we take this clause, location being in station, and work out the active clause coverage criteria for that, then we'll encounter a problem. So out of the 6 clauses that we had in the predicate, now I am taking the major clause to be this one, the one that you see in capital T and capital F here, that column, which means the clause that I'm considering as the major clause is that describes the location of the train, whether it's in station or not in station. So I do the usual thing. I work out the conditions under which this as the major clause determines the predicate. Based on that conditions, I assign true false values to all the minor clauses. So this table describes in station as the major clause. The first column says in station is true. Second row says in station is false. That is, negation of in station is true. And then we assign true false values to the rest of the minor clauses. The major clause in station is also assigned true false values, which is depicted in capital letters here. Now, if you carefully study this table and understand the realistic meaning of what a train should be. So let's say a subway train is going through a subway. Can it be the case that can you ever get a case where the subway train is both inside the station and both inside and in the tunnel? That's not possible, right? Either it's parking in the station or it is moving between two stations and along the way it is inside a tunnel. But if you study this truth table, there is a situation where the finite state model is neither in station nor in tunnel. If you see this last second row here and look at the column for in station, it is false. Look at the second row here, look at the column for in tunnel, that's false. So where is the train? Right? So clearly this is not possible. One way to interpret it would be to say that this is an infeasible test requirement because it says that both in station and in tunnel should be false. The other way to interpret it would be to say that there is something wrong with the specification of the finite state machine. Maybe we should change the specification of the finite state machine. This could also indicate that the machine has been wrongly specified and that there is an error in the model. So when we have logical predicates that label finite state machine transitions as guards, testing it for active clause coverage criteria can reveal interesting scenarios like this, by which one can come to the conclusion that the model is inconsistent or incomplete. One can also come to the conclusion that a particular test requirement is infeasible. Fine. If it is infeasible, then the next step of investigation is why is it infeasible? And that might help us to correct the model and make it a consistent specification. So yeah, so as I told you, test cases for various test requirements need both inputs and expected outputs. So we have to do that. Inputs could be states from which the transitions originate or actions that result in the transitions. Like for example here, for this particular case, the input could be train speed is 0. The train is actually not moving. The platform for that train in that station is on the left hand side. The train is inside the station. Nobody has pressed the emergency stop. Nobody has done override open. So like that, inputs have to be derived from the states or the transitions and the actions that result in the transitions. Outputs are what we expect the finite state machine to do. So they could be states that result from the transition getting enabled. It's a change of state, or actions that happen when this change of state happens. So we have to look at the finite state machine and derive these entities. Finite state machines usually are formally specified, so it cannot be very difficult to derive these entities. So this was a part of what I wanted to talk briefly about finite state machines and logical predicates. So we'll stop here for now. Just 2 more lessons completing logical predicates and we'll move on to the next topic. Thank you.